All right, the last reaction we're going to look at when it comes to radical halogenation is kind of a special case, and that is the case of where we want to add a halogen to an allylic carbon. So let's just review what that position is. So the allylic carbon is that first carbon outside of a double bond. Now, there's a slight problem that arises is if we try to add bromine to an alkene in the presence of light. So if we try to take this alkene and add bromine to it, it's because that alkene is there, it's going to do a reaction that we don't want to have happen if we're trying to do a radical halogenation. What instead will happen is the bromine will add across the double bond. Now, I'm going to talk about this reaction later in another chapter, but the key thing to note is that if I have an alkene here and I add bromine, it doesn't do radical halogenation. So I guess this means, we just go home. I'll stop the recording here and then, we'll call it a day. But as we find with a lot of things where we have these competing reactions, there's usually a workaround. And in this case, instead of using Br2, we're going to use a compound that we call NBS. And here's the structure for NBS. So it's a 5-membered ring with nitrogen there. And NBS stands for N-bromosuccinimide. And what makes NBS so useful for these reactions is that nitrogen-bromine bond is very weak. It easily forms radicals when exposed to ultraviolet light. Oops. There. So we have a nitrogen radical and a bromide radical. So instead, what we can do now is use NBS and light, and that will do a radical halogenation at the allylic position. I kind of glanced over something here, so I'm gonna go backtrack just a little bit and highlight why that position specifically. Because if I look at this, I got a secondary position here and there. Those are kind of the same, but that's secondary as well as that one there. So why is it that I put the bromine at this specific spot and not one of the other ones? Or I should say with the other secondary position. So why not at the green place there, at that green carbon? Well, again, what it comes down to is the rate determining step. What is the more stable intermediate? Because that will give you the lower activation energy. That's the pathway the reaction will prefer. And so the radical that is formed in this will be an allylic radical, which is more stable than a non-allylic secondary radical. So that's the pathway that is preferred in an allylic bromination. All right, so let's look at an example here. So we're going to take this alkene, react it with NBS and light. So the first thing you need to do is identify where is the halogen going to go. Okay, so whenever you have a double bond, you need to think, okay, it's, there could be a good possibility this is an allylic bromination. So I have an allylic position right there, and I have an allylic position right there. Okay, so which one is going to be the preferred position? Well, this one's also tertiary, and this one's only secondary. So just by the stability of the order stability of radicals, tertiary is going to be more stable than secondary. So the radical that gets formed is going to be this tertiary allylic radical. And then let's imagine that it reacts with Br2. And we get our intended product. That's what we would predict on paper. But something weird kind of happens if we go into the lab and we do this reaction. We get this product, but we also get another product. And you look at this and say, how did that double bond move? Like that wasn't even that other secondary allylic position we were thinking about. So how did we get that double bond to move? Well, let's go back to our intermediate here. Any thoughts about how we could get that to move? Well, let's move it through resonance. Notice what happens now. Through resonance, we get this new radical. And if you look at where that radical is at, that's where the bromine is going to end up. And that's how we get to that second product. Now, we don't know for this specific reaction what the distribution is. Do we have more of one or more of the other? The major product depends on the reaction conditions. And this is an example of kinetic versus thermodynamic control. So this is something that was talked about in the last unit about how one reaction could lead to two different products depending on what the reaction conditions are. And if you look at the first product here, this first product is the kinetic product. Why is that? Well, remember how do you figure out the kinetic product? It's the one that comes from the more stable intermediate. Well, this intermediate right here is tertiary. The other product here is the thermodynamic product. Now, why is this product more stable? Remember, thermodynamic product is the product that is more stable, not the intermediate, but the product. So I'm going to kind of jump ahead. We haven't talked much about alkenes, but when we do, one of the things we're going to talk about with alkenes is how we determine their stability. This alkene here has 1, 2, 3 carbon groups directly attached to this double bond. We say that alkene is more substituted. Now, compare that to the other one. The other alkene has 1, 2 carbons directly attached to the double bond. So this one is less substituted. The more substituted alkene is the more stable alkene. So unless we know the temperature conditions, we can't really predict what product is going to be more of. You should, though, be able to determine the kinetic product and the thermodynamic product through this method. Okay, let's do another example of this. So let's look at this alkene. And we're going to react it with NBS and light. Okay, so number one, you have to figure out where is the bromine going to go? Well, in this case, we don't have two allylic positions. It's either here or here, and those are exactly the same. Hopefully you can recognize that. Okay, so putting it on one side is the same as the other. So let's draw that allylic radical. Now, whenever you deal with an allylic radical, you always need to think about resonance. That's the second thing. First thing was figure out where it's supposed to go. Secondly, think about resonance. So I could do a resonance form. That puts the radical here. Now what we're going to do is finish these reactions off, or I should say these intermediates. We'll react them with the bromine, each of them with bromine. So this one will react with one of the bromines. And that's where we would expect it to go. That's the allylic position. But this one down here, we got to this radical through resonance. And that gives us a different product. Now, the final question on this is, which of these is the kinetic product and which of these is the thermodynamic product? So how do you find the kinetic product? Well, you look at the intermediates. Okay, so look at these here. Look at those two intermediates. Which one is more stable? Well, this one's a secondary allylic, and this one's a primary allylic. So the secondary allylic is more stable, which means this is our kinetic product. Now, in order to decide the thermodynamic product, we have to ask ourselves, which is the more stable product? Well, this alkene has two carbons directly attached to the alkene. This one over here has 1, 2, and 3. So the second product there, the one in black, is more stable, and so that's the thermodynamic product. Now, before I end, I want to talk just a little bit about a special type of bromination or radical bromination. That's when we deal with the benzylic bromination. With the benzylic bromination, the bromine prefers to go to the benzylic carbon because that radical is resonance stabilized, but you only get one product. The bromine only goes here to the benzylic carbon, nowhere else on benzene. And if you ask why, I'm just going to say I'll talk about it in somewhere down the road in the semester. But for right now, just kind of take my word for it that if you do a bromination on a benzylic carbon, it only goes to that carbon. There is no other product. There's no resonance that we're going to draw to move the radical around and get the bromine there at the new place. It's only going to go to that benzylic position.